Welcome to the class. Today we're going to have a look at the third lesson in chapter 10. Going to have a look at two topics today. They are electromagnetic radiation and polarization of light. Okay, first of all, let's have a look at the electromagnetic radiation. In early decades of the 19th century, discoveries by scientists such as Hans Christian Ørsted, Andre Marie Ampère, and Michael Faraday established the basic relationship between electric and magnetic fields. Other scientists then worked on extending electromagnetic radiation theory to related phenomena. The electromagnetic radiation consists of interacting electric and magnetic fields that travel at the speed of light. Some examples are visible light, X-rays, infrared light, ultraviolet light, and gamma rays. One result of this work was the discovery of how electromagnetic waves could travel through space. Faraday's law describes how a changing magnetic field by itself can produce an electric field. Many physicists wondered if the reverse were possible, whether an electric field by itself could produce a magnetic field. Scottish physicist and mathematician James Clerk Maxwell, as shown here on the left, hypothesized that this was possible. He proposed that a changing electric field produces a magnetic field. Maxwell expressed his theory of electromagnetism in four equations, generally called Maxwell's equations. The key ideas that his equations express are the following. Here. First, electric charges in space produce an electric field, and currents produce a magnetic field. Magnetic field lines form continuous closed loops that have neither a beginning nor an end. Electric field lines always begin and end on charges. Third, a changing electric field produces a magnetic field. And last, a changing magnetic field can produce an electric field. The symmetry of this relationship between electric and magnetic fields led Maxwell to an important conclusion. In 1864, he predicted that the existence of repeated motions or oscillations between electric and magnetic fields. Moreover, he believed that these would take the form of electromagnetic waves traveling through space. Maxwell devised a series of equations that allow him to calculate the speed of propagation of these oscillating electric and magnetic fields. From these equations, he was able to determine that waves travel at the speed of light. Heinrich Hertz confirmed these predictions in 1887 when he discovered radio waves and verified that they obey Maxwell's equations. The changing fields of an electromagnetic wave can be produced by an accelerating electric charge. In practice, this could be from an oscillating current in a coil or from charged particles that change velocity in some other way. If periodic motion produces the changing fields, the frequency of the electromagnetic wave is the same as the frequency of the current producing it. Faraday's law explains one important property of these waves. According to Faraday's law, the direction of the electric field, which is denoted by epsilon, is perpendicular to the direction of the magnetic field, which is always denoted by uppercase letter B, that produce it. Similarly, the magnetic field produced by a changing electric field is perpendicular to the electric field that produced it. Therefore, the electric and magnetic fields in an electromagnetic wave are perpendicular to each other, which is shown here in this figure, figure 2. In addition, the direction of travel or propagation of an electromagnetic wave is perpendicular to both the electric field epsilon and the magnetic field B. And the two fields oscillate in phase. So in a summary, there are the three central properties of electromagnetic waves are as follows. First, an electromagnetic wave has both an electric field and magnetic field. Second, the electric and magnetic fields are perpendicular to each other and oscillate in phase. And third, the direction of propagation of the wave is perpendicular to both epsilon and B. Okay, so next let's have a look at the concept called the electromagnetic spectrum. All electromagnetic waves travel through a vacuum at the speed of light. Researchers have measured this speed. It's designated by the letter C to be approximately 2.9979248 times 10 to the power of 8 meters per second. The measurements are so accurate that as of 1983, the speed of light is not used to define the length of the meter. So in our lessons, though, we use approximate value, which is about 3.0 times 10 to the power of 8 meters per second. That's the speed of light in vacuum we'll use in the whole lesson here. Researchers classify electromagnetic waves according to their wavelengths, denoted by lambda, and frequency, denoted by letter F. The wavelengths and frequency are related to each other through the universal law equation. We have already talked about this, which is the speed equals frequency times lambda. V equals F lambda, right? The universal wave equation applies to electromagnetic waves as well as to mechanical waves. However, for electromagnetic waves, we use C to represent speed instead of V. A longer wavelength corresponds to a lower frequency. So here, as you can see in figure 3, it shows the frequencies and wavelengths of the parts of the electromagnetic spectrum, which is a range of all possible electromagnetic waves. The lowest and highest frequencies have no specific lower or upper limit. The assigned names in different frequency ranges reflect how the waves are typically generated and how they interact with matter. So in this diagram, you can see that the wavelength increases from top to bottom and frequency increases from bottom to top. However, this is arbitrary. Some diagrams of the electromagnetic spectrum shows the opposite. Okay, radio waves of all types have frequencies from as low as a few hertz to over 10 to the power of 12 hertz. The corresponding wavelengths vary from about 10 to the power of 8 meters to less than a millimeter. Radio waves are normally produced by an alternating current, or AC current, attached to an antenna. AC current in an antenna oscillates with time. The moving charges in the antenna accelerate as they oscillate. In general, when an electric charge accelerates, it produces electromagnetic radiation. The frequency of a radio wave generated in this way is equal to the frequency of the current. Microwaves have frequencies between about 10 to the power of 9 Hertz and 10 to the power of 12 Hertz. The corresponding wavelengths vary from a few centimeters to a few tenths of a millimeter. Microwave radiation interacts strongly with water molecules. Since most foods contain water, microwaves can be quite useful in the kitchen. Microwave ovens generate radiation with a frequency near 2.5 times 10 to the power of 9 Hertz. Water molecules readily absorb the energy transmitted by waves of this frequency. As the water molecules absorb this energy, they begin to vibrate. Molecular motion, including vibration, involves the transformation of potential energy within the molecule into thermal energy. This is a way in which microwaves heat food. On the other hand, infrared radiation falls in the frequency range, as you can see here in this figure, from around 10 to the power of 12 Hertz to about 4 times 10 to the power of 14 Hertz. Satellite cameras that are sensitive to infrared radiation are useful for monitoring Earth's weather, which is shown here in figure 4 on the right. Infrared radiation interacts strongly with molecules and is absorbed by most substances. Vibrating molecules can produce infrared radiation, as can electrons undergoing energy transitions within an atom. So, next, let's have a look at the visible light. Visible light is the part of the electromagnetic spectrum that we can detect with our eyes. It has a narrow frequency range from about 4 times 10 to the power of 14 Hertz to near 8 times 10 to the power of 14 Hertz, as you can see here on the left in this figure, corresponding to wavelengths from about 750 nanometers to 400 nanometers. The color of visible light varies with this frequency. Light in the lowest frequency range with the longest wavelengths appears red. Increasing frequencies correspond in sequence to red, orange, yellow, green, blue, indigo, and violet. White light is a mixture of all these colors of light. Many sources of visible light, such as incandescent light bulbs, produce radiation with a range of frequencies. Some sources, like lasers, produce light of only a single wavelength, which is shown here in figure 5. All right, next, the ultraviolet light, or UV light, has frequencies from about 8 times 10 to the power of 14 Hertz to 10 to the power of 17 Hertz, corresponding to wavelengths from about 3 nanometers to 400 nanometers, which you can see from this figure on the left here. Ultraviolet radiation stimulates the production of vitamin D in the human body. Nearly all other biological effects of UV radiation are harmful. Excessive exposure to UV light can cause sunburn, skin cancer, and cataracts in the eyes. As shorter wavelengths, the damage to exposed human skin increases. The UV portion of the spectrum is commonly subdivided into several regions, including UVA, UV/A, UV/B, and UV/C. UV/C radiation has the highest frequency and greatest potential for damaging tissue because it has highest energy. Fortunately, ozone in the Earth's atmosphere absorbs UV radiation more strongly at shorter wavelengths. So most UV/C radiation from the sun does not reach Earth's surface. Okay, so as we go from bottom to top, next range is X-ray, right? Let's have a look at the X-rays. X-rays have frequencies of approximately 10 to the power of 17 hertz to 10 to the power of 20 hertz, with wavelengths of about 0.01 nanometers to 10 nanometers. German physicist Wilhelm Röntgen discovered X-rays in 1895 and found that he could use them to form images from inside living tissue. X-rays passing through soft tissue blanken a photographic plate when the plate is processed, while the places where bones observe the X-rays remain relatively clear. X-ray can show bone fractures, such as in figure 6 here. All X-ray images use this method until the 1970s, when researchers developed a new technique called computed axial tomography, or CAT or CT. A CT scan takes many X-ray images at many different angles and then uses sophisticated computer analysis to combine these images into a three-dimensional representation of the object. This allows medical professionals to accurately measure the shape and the size of bones, tumors, and so on within the body. Although X-ray imaging is valuable, excessive exposure to X-ray radiation can be harmful. At high exposures, X-rays can damage DNA molecules, which can then cause cancer and other serious disease. Okay, so let's get back to the figure on the left. At the very top of the spectrum shown here is the gamma rays. The gamma rays lie at the high frequency end of the electromagnetic spectrum here, with frequencies above about 10 to the power of 20 hertz, and wavelengths less than about 10 to the power of 12 meters. No precise boundaries exist between the X-ray and gamma ray parts of the spectrum. Energy transformations that occur within the nucleus of an atom, such as nuclear fission in nuclear power plants and nuclear fusion in the sun, produce gamma rays. Gamma rays also reach Earth from sources outside our solar system, which is shown here in figure 7. Okay, so next, let's have a look at a quick quiz, which shows us how to calculate the frequency, wavelengths, and energy of electromagnetic waves. Okay, consider a question like this. Microwaves with a wavelength of 1.5 centimeters carry television signals using a sequence of relay towers. A, can you determine the frequency of the microwaves? Question B, how much time does it take for a microwave signal to travel 5.0 times 10 to the power of 3 kilometers across Canada from St. John's, Newfoundland to Victoria, British Columbia. Okay, I'll give you 3 minutes to consider this question by yourself, and then we'll have a look at the solution together. Okay, let's have a look at the solution together. In question A, we know the wavelength of the microwave is given to be 1.5 centimeters, which is 1.5 times 10 to the power of -2 meters, right? And we know the speed of the microwave is actually c, which is about 3.0 times 10 to the power of 8 meters per second, right? Therefore, the frequency equals c over lambda, which is 2.0 times 10 to the power of 10 seconds to the power of -1, right? Or 2.0 times 10 to the power of 10 hertz. So the frequency of the microwave is 2.0 times 10 to the power of 10 hertz. In question B, first we know the total distance the microwave to travel is 5.0 times 10 to the power of 6 meters. And we need the time delta t. So delta t equal total distance d over the speed of the microwave c. Put all the values in, we know the time taken for the microwave signal to travel for this distance is approximately 1.7 times 10 to the power of -2 seconds. All right, next, any questions? Okay, no questions. Let's consider another quick quiz. Here, a electromagnetic wave in the form of an X-ray transfers its energy to an electron to change its state. The energy of the electromagnetic wave is proportional to its frequency. Suppose the X-ray has a wavelength of 0.025 nanometers. How does the energy of the electron transition compare with that of 540 nanometers visible light? Okay, I'll give you 3 minutes to quickly consider this question. Then we'll have a look at the solution together. All right, have we finished? Okay, let's have a look at the solution together. So we want to find the ratio of energies, which is the ratio between E X-ray over E visible light, right? Okay, the given information says the energy is proportional to its frequency, right? Therefore, we know the ratio between E X-ray over E visible light is equal to F X-ray over F visible. On the other hand, we know F X-ray equals C over lambda X-ray, and F visible is C over lambda visible. Therefore, we have E X-ray over E visible equals lambda visible over lambda X-ray, right? So put these two values in, we have the ratio between the energy of the X-ray and the energy of visible light equals about 2.2 times 10 to the power 4. For the electron transition. Any questions? All right, if no questions, let's take a 10 minutes break. And after that, we'll have a look at the last topic of this chapter, which is polarization of light. Okay, and take a break now. All right, next, let's have a look at the concept of polarization of light. Electromagnetic waves have electric and magnetic fields that are perpendicular to each other, right? And to the direction of propagation. These fields can take many different directions and still be perpendicular to the direction of propagation. When you describe an electromagnetic wave, you need to include the direction of the electric field as well as the amplitude, frequency, wavelength, and direction of propagation. These directions determine the polarization of light, which is the subject of the second half of this lesson. So first of all, what is polarized light? A variety of sources are capable of producing electromagnetic radiation. Examples are the sun, a microwave oven, an X-ray machine, a radio transmitter, and a light bulb. Each source produces electromagnetic waves that transmit energy. The polarization of electromagnetic waves describes the way in which the electric field is oriented relative to the direction of propagation. The light waves in polarized light vibrate in a single plane. A mixture of light with different waves and different directions of propagation is called unpolarized light. In other words, a source of light creates oscillating electric and magnetic fields perpendicular to each other that move away from the source. Light can also be a mixture of polarized and unpolarized light, called partially polarized light. Polarization occurs when you block one of the axes of light oscillation with a polarizer, which is shown here in figure 1. A polarizer is actually a filter or device that allows only light with an electric field along one direction to pass through. If you do not block any of the axes, then the light remains unpolarized. Many applications make use of the polarization of electromagnetic waves. For example, sunglasses use filters to block glare reflected from horizontal surfaces, such as the surface of a lake. Materials such as glass and plastic have different indices of refraction or different polarizations of light. The plastic instruments shown here in figure 2 produce a colorful display when viewed through polarized sunglasses. This effect has practical uses in analyzing stresses to identify where structural failure might occur. Okay, next, let's have a look at generating waves with specific polarizations. Radio stations can generate waves with specific polarizations by using various antenna configurations. Light that is entirely polarized in one direction that is perpendicular to the direction of propagation is said to be linearly polarized or plane polarized. Many natural phenomena such as reflection change unpolarized light to partially polarized light. The amount of light reflecting from a surface for each angle of incidence typically depends on whether the electric field of the light is along the surface or perpendicular to the surface. This is why light reflecting from road and water surfaces is typically partially polarized. Light from the sun encounters small particles that scatter the waves. Shorter wavelengths are scattered more than longer wavelengths, which is why the sky appears blue. As a result, the sky often appears more vivid when viewed through a pair of polarized sunglasses, which is shown here in figure 3. The degree of polarization depends on the relative orientation of the viewer, the source of the light, and the direction of the sky being viewed. Okay, next, let's have a look at the concept of polarization by selective absorption. Ordinary unpolarized light can act as a source of polarized light if you pass it through a polarizer. The direction of the electric field that the polarizer allows through is the transmission axis of the polarizer, which is shown here in figure 4. Light that leaves the polarizer is always linearly polarized along the direction of the axis of the polarizer. One example of the polarizer, called Polaroid, consists of a type of film used in instant cameras to generate developed film images. Polaroid film is a plastic sheet. It absorbs light when the electric field is perpendicular to the transmission axis and transmits light when the electric field is parallel to the axis of the polarizer. Polaroid film contains molecules that selectively absorb light, whose oscillating electric field is along the direction of the molecules. Light with an electric field that is perpendicular to the direction of the molecules passes through. The result is that the light passing through the film is linearly polarized, making detecting polarized light in nature easy. So how can we determine the strength or intensity of light passing through a polarizer? Recall that intensity is related to wavelengths. The shorter the wavelength of light, the greater is its intensity. Consider what happens when the incident light is at an angle theta with respect to the polarization axis of the polarizer. The component of the electric field that is parallel to the polarizer is given by epsilon in times cosine theta. The intensity, usually denoted by uppercase I, of the light is proportional to the square of the magnitude of its electric field vector. So the transmitted intensity is related to the incident intensity by a relation called Malus laws, which is here, I out equals I in times cosine theta squared. The SI unit for intensity is candela. To determine the proportion of unpolarized light that passes through a polarizer, we can calculate average intensity using Malus laws over all possible incident polarization directions. As we might expect, only half of the light passes through the polarizer. Therefore, we have I out equals 1/2 times I in. If we wanted to verify that the light from the first polarizer is indeed polarized, we could pass it through a second polarizer called a analyzer, which is shown here in figure 5. When the analyzer in figure 5 is oriented at 90 degrees to the polarizer, no light passes through. As the analyzer is rotated through 90 degrees in either direction, the light intensity increases to its maximum value. The variation of intensity with rotation of an analyzer indicates that the state of the polarization of the light reaching it. We can use a similar arrangement to observe how some materials rotate the direction of polarization by observing the analyzer to determine the minimum transmission when the sample is between the polarizer and the analyzer. All right, next let's have a look at another type of polarization, which is polarization by reflection. So here in figure 6, an unpolarized light wave strikes the flat surface of a non-metallic material at an angle of less than 90 degrees, or not normal to the surface. Upon impact, the light oscillating electric fields evaporate within the surface of the material. This in turn produces new outgoing light waves. Some of these new waves reflect from the surface and some refract into the material. Like all electromagnetic waves, the electric field of the incoming light waves oscillates in all directions that are perpendicular to the direction of propagation. Thus, some of the electric field oscillates parallel to the surface of the material. Most of it oscillates in directions that are partially parallel and partially perpendicular to the surface. Light waves that penetrate the surface of the material transfer their energy to some of the electrons within the material. This, in turn, causes those electrons to begin to oscillate, which in turn produces electromagnetic or light waves. Some of these waves vibrate parallel to the surface, which means that these waves also vibrate perpendicular to the direction of the reflection. These light waves encounter no obstacles when radiating in that direction and are free to produce a reflected wave. However, light waves that vibrate partially perpendicular to the surface do not vibrate completely perpendicular to the direction of the reflection. Since an electric field must oscillate perpendicular to the direction of reflection to propagate a wave in that direction, these light waves cannot radiate as effectively. The result is that some of the light from these waves propagates in the reflection direction, and some of it refracts into the material. The overall effect is that the light reflecting from the surface is partially polarized along this direction parallel to the surface. The relative intensity of the reflected waves depends on the angle of the incidence. So the degree of the polarization of the reflected light depends on the angle of incidence. At some particular angle of incidence, called the Brewster's angle, the direction of the reflected portion of the wave is perpendicular to the direction of the refracted portion of the wave, which is shown here in figure 6. maximum polarization of the reflected light occurs at Brewster's angle. We can calculate this angle using Brewster's law, which states that the tangent of Brewster's angle equals the ratio of the indices of the refraction, or tangent theta b equals n2 over n1. At this angle, part of the electric field of the incident light oscillates along the direction of the refraction. The photons that penetrate the material cannot radiate in this direction, so that portion of the incident light is not reflected at all. Meanwhile, the part of the light that oscillates parallel to surface keeps reflecting. Thus, at an angle of incidence equal to Brewster's angle, the reflected light is 100% polarized. Okay, so this is the second type of polarization we introduced in this lesson. Next, let's have a look at another type of polarization, which is polarization by scattering. So as you can see here in figure 7, it shows that sunlight, which is unpolarized, can become polarized by scattering. That is, after it is scattered or dispersed after collisions between molecules in the atmosphere. Figure A shows an unpolarized wave of sunlight approaching in a molecule in the atmosphere. When the wave hits the molecule, energy is transferred from the light wave to the molecule. This causes the positive and negative charges within the molecule to oscillate. Figure 7b and 7c show this motion for light polarized in two different directions. In figure 7b, the direction of polarization and the direction of the electric field are vertical. Therefore, the molecular charges vibrate up and down and produce new outgoing waves that are also polarized vertically. These outgoing waves are called scattered waves. Figure 7c shows how the molecular charges move when the incoming light is polarized horizontally. The charges now oscillate in a horizontal direction and again produce scattered light waves. Since vibrating charges do not radiate light waves in the direction that the charges move, no scattered light reaches the observer looking along the vibration direction. Now combine the results in figure 7b and 7c to understand how polarized sunlight is scattered. The part of this light that is polarized vertically scatters to the observer, but none of the horizontally polarized scattered light propagates in the observer's direction. Hence, the light that reaches observer is said to be polarized by scattering. Okay, next, let's have a look at optical activity and liquid crystal displays, or LCD. When linearly polarized light passes through certain materials, the material rotates the direction of the light polarization, which is shown here in figure 8, in an effect called optical activity. Materials that are optically active usually contain molecules with a screw-like or helical structure. Simple sugars such as fructose and sucrose are examples of optically active molecules. The thin, flat displays on wristwatch, cell phones, and many other devices called liquid crystal displays, or LCDs, make use of polarizers to create optical activity. Here, figure 9 shows how LCDs work. A polarizer linearly polarizes the incident light, which is shown here in figure 9a. The polarized light then passes through a film that contains the optically active liquid crystal. The long screw-shaped molecules in the liquid crystal rotate the plane of polarization by 90 degrees so that the outgoing light can pass through an output polarizer. To turn off the display, a circuit applies a voltage to the liquid crystal, aligning the molecules in such a way that they no longer rotate the direction of polarization, which is as shown here in figure 9b. The light that comes out of the liquid crystal is then polarized at 90 degrees relative to the output polarizer. So no light is transmitted and the display appears dark. By applying different voltages to different areas of the liquid crystal, an LCD device can fold various patterns of light and dark regions corresponding to letters or numbers. This is how the display of a wristwatch, a cell phone, and an MP3 player, as well as other similar displays, form the letters and numbers that we see. We can tell that the light from an LCD screen is polarized by placing a polarizer like your sunglasses in front of the glass, in front of the screen. Okay, so that's the end of today's lesson. I hope you learned something today. And I'll see you next time.